Hello there. So today we're gonna see kth largest element in an array. So this is a pretty straightforward algorithm where we can find the largest element and the kth largest element. But here in this video, we're gonna see three different algorithms we are gonna use for this particular problem with comparing their three time complexities and why we are choosing which algorithm and moving from worst case to best case. So let's discuss all this in this video. So let's see what are all the inputs they have given for the problem. They have given an integer array and an integer k. So here we want to return the kth largest element from this array. So the first technique or algorithm we're gonna use is sorting. So here once the array is sorted, it is very clear where the second largest element is there. So the first largest element is at the last position as the array is sorted, and the second largest element is at the last but one position. So here our output is 5. For example, if we want the third largest position, it is from the third place from the last index. So clearly, if you identify at what index, at what place the kth largest element sits is at k elements iterated from the reverse order of the array. That is at the position num dot length, that is the array dot length minus k. So for example, we have to find the second largest element. Where is our second largest element resides? At the fourth index. So size of our array is 6 and our k is 2. So at the fourth position, our second largest element is there. By using the simple logic, we just gonna determine where our kth largest element is. So our code goes like this. So for that, it is a two-line code where we are going to use a predefined function to sort our array and then return the number present at the position nums.length minus k. So it is a pretty straightforward solution whose time complexity is order of n log n. So it is pretty simple. So how to improvise this a bit more in terms of time complexity? So the next concept or algorithm we're going to take is heap or min heap, we can say. So min heap, let me explain the concept of min heap. We are having a heap, min heap. It is going to hold the kth largest elements only. For example, let's take this array. I am going to store only the kth largest elements. That is, the capacity of this heap is k. Here in our example, the capacity of the heap is 2. So it is going to hold only two largest elements. So first number 3. There is nothing in the heap. 3 enters. So the second number 2. It can hold two numbers. So the 2 also enters. The third number is 1. 1 enters. But the capacity is 2. The capacity of the minimum heap is 2. So it cannot hold the minimum. There is no space for the minimum element in the heap. Since it is a min heap, it holds only the two largest elements. So the 1 is getting removed. So the next number 5 enters. So 5 is entered. So the capacity is again 2. It is going to take away the minimum element out of the 3. So it is going to take 2 out. So here we have 3 and 5 in our minimum heap. So the next number is 6. The 6 enters. There is no space for the minimum element. So it is going to take away 3. So we have 5 and 6. Next the 4. 4 enters and the capacity is 2 again. We're going to take away 4 since it is the minimum element. So now the heap is having only the two largest element from the array. So this is how our minimum heap works. So now we're going to take the second largest element or the largest element from this minimum heap easily. So we're going to use a data structure called priority queue to work on this minimum heap. So what does a priority queue does? A priority queue will insert every value in ascending order. For example, first it enters 3 here in the queue. Now at the next iteration the queue becomes 3 and 2 in the front, because it inserts the element in the ascending order. We set one more code, like if the size of queue exceeds k, that is the size of our minimum heap, then poll or remove the element. Remove the element which is first inserted. Which will be first inserted? That will be which will be at the top of the queue. That will be the minimum element, because this is the priority queue. So again, at the third iteration the queue becomes 1, 2, 3. It goes and check the condition. Yes, it exceeded the size. So let's remove the topmost element. So it removes 1. So at the next iteration it will become 2, 3, 5. Yes, again it checks the condition. It exceeds the limit. So remove the top element. The same way it iterates and inserts 6 and take away 3, inserts 4 at this position and take away 4. So 5 and 6 remains. So next, if you remove the element at the last, it is going to remove the least element from the queue, that is 5. That is our kth largest element. So let's see how to implement that in code. So yes, getting to our problem in Leetcode, I have already submitted my sorting code where the results are accepted. So now I'm gonna type in my heap code. For that, I'm gonna declare a priority queue. And this queue of size k. Now I'm gonna iterate my array and add every element in my priority queue. So I'm adding, and it will be saved in the ascending order. So now once the elements are added, I'm gonna check if q dot size is greater than k. If q dot size is greater than k, then I'm gonna remove the top element from the queue. So q dot poll. So every time a new element is added, it is gonna remove the top element, which is the least element from the k. So now the queue is with the k largest elements from the array. So now finally I'm gonna seek the last top element, which is the kth largest element from the array. Let's run the code. Okay, I didn't return, sorry. So yes, the solution is accepted. If you see, the runtime is 4 milliseconds. So now, so this algorithm will make the time complexity from O log n to order of n log k. So this is the time complexity of this heap algorithm, which is pretty a better time complexity. Now let's see how further make it better. So for that we are going to partitioning. So we are going to partition using a quick sort. So let's have a quick go through of how quick sort works. So let's see this example. The basic function of quick sort is selecting a pivot element and making the partition the array like the numbers less than pivot element should be on the left side of the element, and the numbers greater than pivot element should be on the right side of the element. So let's consider this example. Let us take the right hand side. This is the left side and the right side of the array. Let's select the right side element as our pivot element. So now we are going to partition this array with pivot element, that is the numbers less than pivot element will be on the one side and the greater than numbers will be on the other side. For that we're going to have two pointers, I and j. So what is the job of the pointers I and j? So the job of the pointer I is to remember the last position that an element was placed in that was less than the pivot. That is, it will remember the position of a number of the range less than the pivot number where the numbers less than pivot number ends. So if you're not getting it, just come along, we'll understand as we go through this example. So the purpose of the j element is, this is a scanner element, so it is going to scan the array from the range 0 to n. So it moves every time, it iterates every time it encounters the new element, and I iterates every time there is a swap. So when there will be a swap, it just first compares the element with pivot, and if the number is less than pivot, then the swap between I and j happens. So clearly, what are the steps? First, j is going to iterate the array from 0 to n, and it compares array of j with the pivot element. If it is less than the pivot element, then swap happens between I and j and I increments. If it is greater than the pivot element, just I goes to scan the next element. So there are three steps. It compares a of j with pivot, and based on whether it is less than or greater than, it increments I and swap happens. So let's iterate this example to see how quicksort works. So yes, considering this example, our pivot is 7 and we're gonna iterate from 3 to 9, and our I and j are in the same place for the first iteration. First we're gonna check whether 3 is greater than or less than 7. 3 is less than 7, so the swap happens. If you check, I and j are in the same position, so there is no change. So now j moves to next, because the j is a scanner element, we checked the 3 already. So now moving on to the second element, that is 4. So now our j is at 4, it compares 4 and 7. So whether 4 is less than or equal to 7, 4 is less than 7. So now the swap happens between 3 and 4. So now if you see, 4 and 3 are swapped, and let's move I, increment I to the next position. So I is moved. Now j will also move, as this is our scanner job. So now comparing a of j, that is 5 and 7. 5 is again less than 7. So now the swap happens between I and j. So now the swap happened. As the swap happened, we increment I and j as well, as this is the scanning element. Now we are comparing 8 and 7. 8 is greater than 7, so we are not swapping the element but just moving the j. So now j is in this position. We are comparing 9 and 7. 9 is again greater than 7, so we are not swapping anything. I stays the same and j moves. So now the iteration is completed. Now if you see I, from I, the elements here are less than the pivot element, and the element after I are more than the or greater than the pivot element. So if you remember what I said, the job of I is, it is going to point at the element where the numbers less than the pivot element ends. So here in this position, the numbers less than the pivot element ends. This is the index where the last element less than the pivot element exists. So now we are going to swap I plus 1 with position 7. That is, I plus 1 is 8. I mean, the number at index I plus 1 is 8. We're going to swap it with our pivot element. Now our array becomes 4, 5, 3, 7, 9, and 8. So this is at end of our first iteration, our array looks like this. So if you observe, it is numbers less than the pivot element, it is number greater than the pivot element, and this is the final position of the pivot element. That is, this number will not move till all the iterations are complete. See, you manually sort this array. This array will become 3, 4, 5, 7, 8, and 9. So this fourth position is the final position of 7. So whenever we are taking an element as pivot element, at end of that iteration, it comes to its original position. So now what does a quicksort do? It just partition the array into 2 and further perform quicksort for these 3 elements and perform quicksort for these 3 elements and finally combine and end up with the sorted array. So this is the concept of quicksort. In our example, what we are going to do, if you are, once the first iteration is done, you can see this is the output of the array. So where does our kth largest element exist? We just calculated in our first example by n minus k, where n is the length of the array, k is the kth element, and at this index our kth largest element exists. So here the index of 7, that is our pivot element, is 4. So our kth second largest element exists in this example here, that is at the index 5. So we know at which position our output exists. So this is the position we need to take. Now we reach this position. Let's check whether 5 is in this range or at this range. We can clearly say 5 is at the second half of the array. So we can simply ignore this part and only use quicksort and the second half of the array to find our output. So clearing all this mess, let us again go through an overview in a clear screen. So now once we sorted the array in our first iteration, here this 7 as at its final position, that is our I was here and now at I plus 1 our 7 is placed or our pivot element is placed. Now where will our second largest element be there? It will be there in the 5th position for our example because it was k is equal to 2. So our 7 is at 4th position. It just check whether our output position is in this range or this range. So clearly it is in the second half. So we're gonna just apply quicksort in this alone to find our output instead of completely sorting the whole array. So if you compare our previous example and this example, in our previous example we'll completely sort the array so that at the end we can find any, for example, the largest element or 5th largest element or 4th largest element. We can simply take the output, any of the output from the sorted array. But here we are not going to do that. We just want the kth largest element. That is the only thing we want in this problem. We don't care about the other elements whether they are sorted or not. So let's see the example given in our problem and look how it works. So this is the example given in our problem. Let's take the example and work on it with quicksort. So here let's take 4 as our pivot element. As I said, I is here and j is here. It is gonna check whether 3 is less than or equal to 4 or not. It is less than, but no swap happens. J moves to this position and check whether 2 is less than. Yes, 2 is less than, so it swaps. So 2, 3, 1, 5, 6 and 4 remains here. So at our next Next, I would have been moved here and j would have been moved here. So it checks 1 is again less than 4. It swap I and j. So now the array becomes 2, 1, 3, 5, 6. 4 stays the same. And again, our I would be here and j would be here. So it checks whether 5 is less than or greater. It is greater than, no change happens. So j moves here. 6 is greater than 4, so no change happens. The iteration ends. At the end of the iteration, it looks like this. Now we are going to swap the 4 with I plus 1 position. So now our I is at this position. So here it ends. The numbers less than 4, right? So less than 4 are here, greater than 4 are here. So now we are going to put its exact position, because this position changes between them, but the fourth position will not change, because once it is placed here, the numbers greater than here are there, less than here are there. So this is the final position. So at the end of the iteration 1, the array looks like this: 2, 1, 3, 4, 5, 6. So where should be our answer? That is, in our problem, the second largest element will be placed at n minus k. That is, n is the size of the array 6, minus k is 2. So at the fourth position, that is 0, 1, 2, 3, 4, here. That is here in this position. So now our I is 3. So let's check whether our 4, that is the fourth position, is within this range or this range. It is clearly within this range. So ignore this and take only this 4, 5, 6 and apply quicksort. Now again in 4, 5, 6, as I said, the time reduces to half every time. Let's consider an example. First, to discuss about quicksort, we took one example: 3, 4, 5, 8, 9, 7. So at the end of our first iteration, we placed our pivot element 7 in the middle, so that the numbers less than this and greater than this separated into a partition. Consider the same example. At the place of pivot element, we have 1. If you compare this array manually, if you see, 1 is the lesser element out of all elements in the array. So the j will iterate completely to find there is no elements less than 1 and swap it before all the elements, that is at the 0th position. So in this case, we have selected a poor pivot. So what it does, if an element is very less than every element in the array, it took n time, that is iterate every element, and then finally it placed its position. So consider the same example: 3, 4, 5, 8, 9, 11. So in this example, if we consider this as a pivot element, it is larger than every element in the array. So it again iterates completely to find there is no element greater than this and place its positions here only. In this case, it takes a lot of time to make the partition. So if we are selecting a poor pivot element, then at worst case our time complexity becomes order of n square. So, but occurrence of this condition is very rare. It occurs only if we choose a number very less than the smallest element or the largest element as our pivot element. Hope you are getting it. So to avoid that, we are going to select our pivot element randomly using random function. So what it does, it just select a random index and select random numbers of pivot element. So the occurrence of selecting the smallest element or the largest element as our pivot reduces, so that, as discussed, our time complexity stays linear, order of n. So if you see, our array was 2, 1, 3, 4, 5, 6. In our previous examples, we took the complete array, that is n, to sort, and from that complete array we will find our kth largest element. But here we are just partitioning it and finding in which range our output exists and completely ignoring this range, so that every time it does a partition, its time reduces by half. So further, if we divide this range into half, this again becomes n by 4. So by this, for every iteration we are reducing half of its time. So let's type the code in Leetcode and see. So here we have typed in our MinHeap code already and submitted it. Now I'm gonna work on my quick.